Okay, maybe we should start now. I think the rest can join later on. Hi, so my name is Hatem Akel. I'm an RF application engineer at Ozen Engineering. Thank you for joining this webinar. Several topics will be discussed. This presentation is about signal integrity. So in this tutorial, we will show how to use Ansys tools to do signal integrity with the focus on pluggable transceivers. However, whatever we're going to show today can be applied to so many different fields. It's not limited to SerDes lanes or just to transceivers. So this is the table of contents. As a first step, let's define signal integrity. I wanted to spend a few minutes just defining what's signal integrity. And from there, we will discuss our main goal from this webinar. What are we trying to do? What are we trying to achieve? And I will briefly after that give a small introduction to transceivers for our audience who doesn't know what's transceivers and their standards. What do we mean by standards? Then we will talk about HFSS modeling, and we will share some ideas with you. And finally, we will dig deep into signal integrity and post-processing. Okay. So signal integrity. What is signal integrity? So what do we mean first by when we say we want to reach integrity? It means perfectness, something that is clean and free of damage or distortion. But that's impossible. So what do we mean by signal integrity in real world now? For uh, system engineers, it's a set of specifications that must be met by a communication link or a section of a communication link in order for there to be sufficient communication throughput. This is what we call as like a signal with a low bit error rate, if we are, of course, talking about a digital communication link. That's all what they care about, the specification and the bit error rate. So how about us? How about the RF engineers like us who are using HFSS and Circuit-Designer? It means three things, not just one. It means phase one is identifying and fixing or minimizing any defect in all the components of a communication link. Then phase two is building a reliable communication link by cascading these components. And finally, phase three, which is as crucial as phase one and phase two, which is being able to debug measurements. Today's webinar is all about these three phases, providing you with easy to use tools to do signal integrity professionally and efficiently. So let's talk about this mission. What's our goal from today's presentation? What we are trying to achieve or build is our templates for designers to help them verify their designs against all the specifications. Simply, it will duplicate what you will see in the lab when you measure your product, your transceiver, pluggable transceivers in this case. The templates contain circuits of all kinds and also the plots that you see here to the left, and also you can see them from the tabs. Like we categorize them based on where are they measured. For those of you who are using another tool for this looks very familiar, but the advantage here, you simulate and instantaneously you see the effect on the system, the effect on the bit error rate and signal error rate, as well as the specifications. So for the first time, you will be able to link what you do inside HFSS model and the bit error rate directly, as well as I said, the specification. You will be able to tell what will happen if, for example, I violated one of the specifications. What's going to happen? Like my product is going to blow up in my face. The bit error rate would be very bad, or nothing is going to happen. It's a legitimate question that each one of us has had for many years. Now, this template will answer this question for you in a matter of 1 to 2 minutes. You change a via, and you will be able to see the effect on the bit error rate. However, when we didn't want this template to be simply about specifications, a design template. which is important, by the way. But we want it also to be a debugging tool, a tool that you can use to do debugging while designing and also during measurement, which is, as I said, phase 1 and phase 2 and phase 3. So we added a lots of debugging tools that we will be, and we will be adding more. So this template is for you, by the way. It's free. You can download it and you can use it the way you want. Great. So this is what we want to achieve, and we will talk more about it very soon. Let's talk a little bit about transceivers. What are these transceivers? As I said, this is a small introduction for our audiences who never worked with pluggable transceivers. So pluggable transceivers are devices like they are of the size of your of a USB memory stick. They are used in optical communication link. They are simply RF to optical converters and vice versa. The transceiver has both the transmitter section and the receiver section. These definitions you need to be careful about a transmitter and receiver are with respect to the optical side. The transmitter because it transmits optical signals and the receiver because it receives optical signals. There are other definitions with respect to the RF side, with respect to the host. So you need to be careful. Now, the common ones are always the ones with respect to the optical side. So when somebody mentioned the transmitter of the transceiver, you know exactly what he's talking about. These transceivers comes in so many different forms. I listed here a few features and abbreviations that you will see if you are trying to work with a transceiver or if you want to buy a transceiver. So if we are talking about the length of the optical link, then we are talking about like SR, DR, LR, ER. If we are talking about the size and the location of the pins, like some sort of mechanical dimensions and thermal and power supply, then we're talking about SFP and QSFP and CFP and OSFP. I wrote here a couple of the explanation of some of these definition the terms. Now think about all the possible combination of these, and that tells you how many of them exist in the market. And for each a group of them, there will be a template for it. We are planning to design a template for it. In this presentation, we will be focusing on the QSFP-DD because this is the trend now. DD, by the way, stands for double density version for on the RF side. So DD transceivers like they have 8 TX channels and 8 RX channels versus the one which is not DD that has 4 and 4. Now, if you have 8 channels and you have 25 gigabits per lane, then you're talking about 25 times 8, which is 200. If you are using PAM4, then you are using 50 gig per lane times 8, that's 400 gig. So now you know if they talk about 200 gigabit transceiver and 400 gig, what does it mean? What about these transceivers? So these transceivers, each one of them follow a specific standards. These are documents generated by special technical committees, and these documents describe everything in these transceivers, mechanical, optical, electrical specifications of all kinds. Now, the good thing, like I listed just a few of them here, but there are so many in you can find them in if you Google them. So the good thing about these standards is that they do not just talk about the device itself. They also describe how you're going to measure it, how you're going to characterize it, the reference plane of the specification, the electrical specification, for example, are measured where. And the technical community decided that for the transceivers should be measured after the connector using what we call MCB boards that you see. I just plugged one example here. MCB stands for Module Compliance Board. And the reference points were given names like TP1 and TP4. So TP1 on the transmitter side and TP4 on the receiver side. So you're going to see these names. In fact, even if you look at to the right here, you will find that our templates has these names to indicate to which point that graph belongs to. So I'll talk a little bit about HFS modeling. So this is what we are trying to do, to model are the SerDes line. Like there are so many parts within the transceiver that are not the subject of our discussion today. We're concerned about the SerDes here. SerDes stands for serializer and a deserializer. These are signals. These are lanes that carry one signal, and that signal, in fact, is made or is constructed from hundreds of low frequency, low bit rate signals in kilobits per second. But you have hundreds of them combined together in a TDM fashion, in a time domain fashion, multiplexing, to create one signal, and consequently this signal has a very high data rate, like in gigabits. We're talking, for example, in our application now, we're talking about 112 gigabit per second signal on each one of these channels, in each one of these lanes. Now, the model that I'm trying to simulate here contains the end section of the transceiver, plus the connector, plus the MCB, and I'm just simulating my RF lines. I'm removing whatever is in between to reduce the size of my model. And of course, you will ask yourself, why do I include the connector? Why do I include the MCB in my HFSS simulation? And the answer is because it's the only way for me to verify my transceiver against the specification. Without them, I cannot do anything. If you try to characterize or simulate your transceiver without the connector and the MCB, then definitely we will be doing something wrong. We will miss everything. We will not be able to tell what exactly we're gonna, what do we expect to see when we do our characterization, our measurement. So here, let me go to slide 5. So what I did is what we all do, the traditional things. I took my large model. I'm not gonna simulate the whole large model, and I divided into 3 small sections, and I did the optimization of each alone, made sure that each one is by itself doing very well. In fact, after simulating each section, I would plug it in the template that I was talking about, and I verify the numbers, check for deficiency, and most importantly, check for how much margin I have, like how much each section is taking from my spec. I will show you the models very soon. Great. So until now, everything is fine. But one thing, once we start HFSS and start these applications, the first question that comes to our mind is, when we simulated to which bandwidth? Like, do we simulate it to 40, 50 gig? What do we do? So I created this table just to show you guys that there is not a single answer to that question. So if you see in the, so I wrote a couple of numbers related to different kind of applications. What our concern, what we are talking about today is this column that's in red. But I wanted to show you what's happening with other options that exist and the future ones. This is the future ones. So in the first row here, good enough bandwidth. What I wanted to show you is what the industry is recommending for each type of transceivers. So for our case, for example, they are recommending that the simulation should be extended up to 70 gig, that you should have something really clean up to 70 gig. Do I use that? What about the Nyquist? What about the second Nyquist? What about the third? Do you stop at the 3 dB bandwidth of your channel? Do you stop at the VNA bandwidth? Do you use the rising time, for example, instead? And if you use the rising time, what do you use? 0.35 over the transit time, or 0.5, or 0.65, like some people suggested? As you can see, there are many possibilities. The last row is what we are doing, is what we are recommending when you are doing measurements. This is very important. It's very important that you measure things and that you simulate things at the same bandwidth as your sources and your VNA. Don't try to go beyond that, because then you will not be able to match your measurement to your simulation. You will see something different. So it's very important to have both of them the same when you do measurement debugging. Of course, if you're planning to do TDR, as you all know, I'm using TDR whether to check the impedance of my lines, or because I want to isolate the different transitions and I want to look at them. So in this case, your rising time, your rising time that you need to use has to be at least 1/3 the distance, the minimum distance between any two transitions. And from that 1/3, and that from that rising time, you do 0.35 or 0.5 over the transit time, and that tells you how far can you go in the bandwidth. Now, remember, during design, you can do anything. In general, it's recommended that you extend your simulation to as high frequency as possible. And the trick here is, if your structure has any funny small features, only at high frequencies you can see it. They get exposed. That's a design hint for you to explore. Okay, so now I'm going to stop talking. I'm going to be switching between HFSS and my presentation just to spice things, and also to show you guys the models. So I'm going to show you now what I've been doing. So these are the models. As you can see, I followed all the necessary guidelines. I made it as big as possible. I moved my ports back. I did the de-embedding. Some people, when they do de-embedding, by the way, they try to de-embed their structure to the first disturbance. You are aware now that this is not correct. The field starts changing way before that. So you have to stop before that. The same argument, by the way, applies to the ports. No matter how much we try, there is a discontinuity at the ports. So the de-embedding is not correct. There's a small error that we have to live with. Okay, the right way to de-embed things is to do calibration. We will talk about that maybe in another webinar. So as I said, these are the models. Now, in every webinar, we try always to pass few informations, few ideas to people to help them do their job properly. Things that exist in HFSS, yet we notice that people do not use them. And one of them is clipping, and I wanted to demonstrate it on this large model here, so it will be easy for you to understand the importance of this. So in every model I build, I usually go ahead and add what we call clipping plan. And let me show you how I do that. So you go view, and you go clipping, and you say clip plan, and you say add. Then you specify the center and the normal. And you select a point. Maybe I will select a point here, and I will select the orientation in the Z direction. Usually I create one for each axis, but for now we'll just show one. Let me show you what you can do now by having this. I can grab this and I can go down slowly, and as I go down, it exposes all the internal structure for me. See, I am not going to miss anything. I am not going to guess. I am not going to make any mistake. I will be able to see everything. This is important when you are trying to do simulations for many days, many hours, or many days. Before you do that, like you can do that while you are doing building the model. That's also something good. But this is mainly when you are trying to launch the solver for many days. You don't want to make a mistake. You don't want to miss anything. And how many times it happened that we deleted a via or structure by mistake while we are doing some manipulation, and we end up after a few days discovering that we made a mistake. So this is something that you guys can use to avoid falling into that trap. Okay, so enough HFSS. Back to our slides. Close this guy here. So this is circuit design. Great. I finished building my model. I finished building my model. Now it's time to cascade them. And as I said, the templates, I used it while doing each component, but now I want to see the whole thing together because I am trying to check my design versus specifications. So I build these circuits, and there will be more to be added. I uploaded the linear frequency, the transient, and the I solvers. And as you see, this is the standard I'm trying to verify my design against. As I said, more will be added. And this set of graphs is the template. You see that the formulas that you see to the right, these are all formulas already graphs. We build them for you. We check the formulas for you. We set them up in such a way that you don't need to do anything. You just plug your stuff, and it immediately will do all the collection, all the calculation for you. So in my case, you see, I plugged my three parts in in series. In your case, you can remove these ones, put your own. You can also add the ASIC part. I don't have any ASIC part. I'm assuming that my ASIC part, which is inside the transceiver, to be a perfect 100 ohm termination, which is, we know that's not true. You need to have more accurate results. You need to add the ASIC. So it's a standard way of building models and preparing it to be solved and uploading the right solver. And in the solver, of course, you have to set it the same frequency as within your HFSS model. Now, so what do you expect to see when you open any one of these graphs? So practically what you're going to see is of course, the plot of the graph itself. As you can see here, you're also going to be able to see the formula that we use to calculate that graph. So some of them are simple, straightforward. Others are a little bit more complicated. I would advise you to download this template, even if you are not doing stuff like that, because you're going to learn a lot from the formulas that we used to calculate many curves. There are others that takes like multi-steps to calculate. They are also going to be able to see them. We describe them in details in our template. Not only that, you're going to find also the limit line. So this template is, as I said, for the 802.3 CK standard. So this limit line belongs to that, but you will also be able to see the formula that we use. So consequently, all the information about the standard, all the information about the standards, you don't need to go anywhere to look for them. They are all here. You will be able from here to see all the specifications and all the limit lines all together, of course, in one place. Now, I'm going to use this to give you guys another hint about the results. If you notice here, what I did here is I took my my plots, my curves, and I duplicated them here. This is an important trick for you to protect yourself in case you did the presentation and suddenly something happened and you lost your curve. So what this is going to do is it's going to delete only the solution, but it will not delete the backup. So this is another way to protect yourself. Yeah, you would not be embarrassed in front of your team or your clients or your manager when you try to present something or prove something. You are always 100% sure that you do have the curves. They are there because you made a copy of them. And the way you do copy is just you select these two and you see copy data. Don't do copy definition, because HFSS allows you to do copy definition. That's not what you want. You want copy data. Then on the same graph, you say paste, and it will create a copy of them. What else can you find in this slides? In some slides we put even details of how we created this graph. So this is even more data in details what we did in order to generate these plots with the specifications also and the numbers. So you're going to see a lots of information within this template. So let me show you the circuits. Sure. So I'm gonna bring HFSS again. As I said, I'm trying to do that just to spice things. I don't want it to be always about doing things. So this is my circuit. It all simple as this. So you can see the different circuits, the different structures. And here you can see all the graphs. So if I go results, I'm going to see all my graphs here. But at the same time, you can go to these tabs. And within these tabs, you will see all the graphs cascaded together, depending on where are they. And are they TP1, which is the transmitter? Are they TP4? Are they system tools? I'm going to talk about them. Are they debugging tools? Sorry, they keep changing with me every time I close. So are they debugging tools? What are they? So we classify them for you. And I said, as I said, this looks very familiar to people who are using other softwares. So we have all kinds of plots. We have linear plots. We have bathtub plots like these ones for people who knows bathtub. We have I plots, frequency plots, TDR plots, all kinds. I'm going to try to go through them as fast as I can within the time given to us. All right, so back to the slides. So now I'm going to talk about I'm going to go deep now into pluggable transceivers and talk about the specifications on the transmitter side and on the receiver side, and how we do this as a how we do systems and how we do debugging and what's about the system tools. But as I said before, it's applicable to so many other applications. It's not limited just to transceivers. You just need to change the numbers. So TP1. So what TP1 is, when we try to measure, when we activate our transceiver, and we are looking from the transmitter side. So if you look at from the transmitter side, you are aware that there is nothing coming out the transceiver. It's the transmitter side. It's expecting something. It's expecting a signal from the host. That's why when you look at all the specifications, you will find that most of them or all of them, in fact, they are passive measurements. Differential return loss, differential to common, common to differential, termination mismatch. Termination mismatch is you will find the definition here and also in the graph, is simply a measure of how does the P and N of each differential signal, do they see exactly the same termination inside at the ASIC, at the chip, which is inside the transceiver? And that's why it's measured at very low frequency, because we're not concerned about what's going on in the path. We want to reach the end. We want to reach the chip and see if the termination of the P and N are equal, how much they are equal. So there is a spec on that. And there's the DC common voltage, which is just a measure. This is very, it's almost like a DC kind of, that's why they call it DC common mode voltage. It's a measure of the change in the potential of the reference ground. Like, is the ground that I have outside, is it exactly the same potential as the ground that's the chip or the end where it's receiving my signal? Are they both the same? So that's another spec that we have in the standard, and we need to check it. So that's why you will find these graphs into our plots and how we do the calculation. Now for the TP4 is different. TP4 is the receiver side. Here, as I said, I'm assuming that the lines I simulated in HFSS are remember what I did in my HFSS model is I simulated only 2 lines. And the reason why I simulated 2 lines, because usually in the transceivers, every pair of lines, they are almost duplicated, and you can isolate them by themselves and simulate them alone and get a lot of information. Of course, in the real model, you have to model the 16 channels, because you also want to see the crosstalk between the TX and RX. But for simplicity here, I'm just showing 2. We are planning to build a template, like identical template to this, for the 16 case, and another one for the 8 case, where we isolate the TX alone and the RX alone. But just for the sake of this webinar, we made it only 2 lines in order to facilitate the presentation. So TP4 is on the receiver side. When I activate my transceiver, there is a signal coming out of that transceiver on that side. So yes, I do have the same kind of passive spec that we found on the TX in terms of differential return loss and mismatch and DC common voltage and mode output noise. But also we have more than that, more important stuff now, which is the I measurements. So let me show it to you here. So circuit designer, so we need to measure them, we need to check them. So circuit designer has 2 important solvers for I analysis. Now we are deep into system analysis. One of them is called verify I analysis, and the other one is quick I analysis. So the verify I is the one that calculates the bit error rate or the signal error rate in case of PAM4, and generates the bathtub. So the bathtub is plot along a specific y-axis, like it draws an horizontal line, and it plots the bathtub, and the bathtub tells you immediately where is the point at which the bit error rate is very high, and at what time it crosses a certain point that it's no longer tolerated. So you can select, yeah, so when you do this bathtub, HFSS Circuit Designer allows you to select on which eye. Like, for example, this one, I selected the middle eye to plot my bathtub. But there's an option where you can plot for all the three of them if you want, together on top of each other. So that's available. So how about the quick eye? The quick eye simply displays the PAM4 eye diagram, or the NRZ eye diagram, which is similar to what you guys see here at the bottom corner. That's why we call it quick eye, because it simply plots all the signals on top of each other. That's all what it does. As simple as that. It doesn't do any calculation. But Circuit Designer later on, which is now the post-processing, and upon your request, can do eye calculations and provide you with the eye heights and widths for the three eyes. You see them here. So these numbers are correct. There's nothing wrong with them. But the problem is that they are generic. The built-in calculator within Circuit Designer, within the quick eye, doesn't know your standards. It's not doesn't know them. It's made for all kinds of application. It looks for the optimum height and width, and also what we call the threshold voltage that you see here, which is like the optimum point, the optimum voltages that you can use to say, if this equal to this and it's greater than that or less than that, then I know it's 0. If it's greater than this, then it's 1, and so on. This is what we call threshold voltage. And these are all calculated at the ideal middle point of the eyes. But that's not what the transceiver standard is asking for. So then we needed to do some post-processing, additional stuff. And the stuff that I'm going to tell you about is all done for you within this template. That's the beauty of this template. It's going to do lots of calculations for you automatically. So the standards of the pluggable transceivers have a very stingy way of calculating the height and the width of the eyes. It starts by asking you to determine the 1a-3 contour on the bathtub of the middle eye. So now you know why I plotted the bathtub on the middle eye. Then it used that to calculate the middle point that you see here. There's a middle point. That middle point is officially now the middle point in time for all the three eyes. Yes, it cannot be different for the three eyes. It has to be the same for the three eyes. And it's fixed by this condition, the 1a-3 bathtub. Now, what you're going to do is we need to draw a vertical line. And guess what? Now that the standards is telling us that you need to find out where is the intersection between this vertical line and the 1a-5 now. Not 1a-3, 1a-5 contours. So let's assume that the red ones that you see here are the 1a-5. I'm just assuming that. I'm going to show you in another slide. Then from there, you determine V low and V mid and V up. V low, V mid, and V up are just the heights of the different eyes. So they need to be determined, they need to be calculated at TC mid, not at any point. So if I go to this slide, again, I'm going to show you all of this very soon in HFSS. So what I did here is I plotted these contours, which is the 1a-5. And unfortunately, you need to plot them as contours. So you'll find all the instructions here. And what I did, what the template will do is we'll take these contours and we'll center them at the 0 with respect to the TC mid for you. So it calculates TC mid for you, comes to here, it doesn't allow it to be anywhere, it will center them right in the center. Then it plugs these markers. Now the only glitch we have here is that because this is contour plot is like painting. They are not curves, they are painting that HFSS does here, the display here. So unfortunately the markers do not snap to these curves. So sometimes you need to zoom in and snap them manually. But once you snap them, then you will get the first the 6 numbers that you see here: P1, P2, P3, P4, P5, P6. They are important to us for other calculation. But at the same time, it will give you what is the delta Y here. And it will specify, for example, here, I'm violating the spec. My spec is 40 millivolt. Now I need to be worried. But don't be worried, because here I didn't do any equalization. The standards allow us to do some equalization. I didn't do equalization in this case. I just assume no equalization, whether on TX on the TX side or the RX side, on the host side or the transceiver side. There's no equalization. That's why I am violating violating the spec, because my transmission lines, I made them intentionally very bad. Um, Once you get these 6 numbers and you get the height, now you got the height, now you compare it to the spec, now you know how far you are. You take these numbers and you plug them here, because what we need to know is we need to know the middle point of these numbers. So you just plug the numbers here, and immediately these will be calculated for you, as you can see here. So why do we need to calculate the middle? It's because of the standards again. The standards is saying is that the width of the eye, you cannot measure it anywhere you want. It has to be at the centers that were calculated here. So you need to take the centers. By the way, this contour is another graph. It's called eye width. It's identical to the graph I showed before. It's the same contours, which is 1a minus 5 contours. But now I want my markers to be at the y values specified by these numbers. And as you can see, they are not at the optimum point. They are not where the eye is maximum. But unfortunately, this is what the standards wants from you. By doing this, now you have all the information. Of course, later on, we're going to use P1 and P2 to do other calculations related to other spec, which is the VEC and the eye linearity, as I'm going to show you later on. But this is the procedure. These are the steps. You need to be familiar with this if you are working with pluggable transceivers, that these are the stingy requirements. And this is how our template do the calculations for you. So everything is ready for you. Just as I said, unfortunately, the markers you need manually to move them. But this is it takes me like a few seconds just to align them. By the way, here this table, the good thing here is this table. You click on the Y and you enter it manually. You enter it specific. You don't need to move the markers. You can come here and say, I want the Y to be exactly minus 206.5, and it will align it at 206.5. So it's an easy process. It's not very difficult stuff. So I'm going to talk about system tools. So what are these system tools? Why are we adding additional stuff? So when you measure, when you have your transceiver and you are in the process of measuring it, you have no access to what's inside the transmitter, inside the transceivers. You only have access to what's outside. These ports, we know nothing about them, but during design, we have access to them. And what happens is that your system team, your internal team within the company, they will come to you with additional specifications that are not in the standards. These are things that they want you to measure, to simulate for them, calculate for them, and they will have a specification. They will have limitation on you. They will tell you these numbers shouldn't exceed this, shouldn't do that. Why? Because for so many reasons. Like I can count tens of reasons related to power, related to matching, related to crosstalk, name it. For so many reasons, they want you to be within certain numbers. So we added some of the ones that we are aware of. If you need more, let us know. We're gonna add them. And you see, most of them are return loss, looking from the transceiver, but inside. And we have also the insertion. So the insertion, we cannot measure the insertion when we are measuring the transceiver. When we are measuring the transceiver, you cannot. You have no access to what's going on inside. But as I said, during the design, you have access to the insertion, and they will have lots of restrictions, lot of requests for the insertion, whether it's differential, common mode, group delay, the skew. The skew between the different lines. How much is it? And the skew between P and N. And the way we do the skew here between P and N, we do it in a very precise way. Like, it's not using the physical or using some funny tricks. No, we do a dedicated kind of formula with a lots of derivations in order to be able to calculate that in an accurate way. How much is exactly the skew between P and N, as seen by the outside world or as seen by the transceiver itself. Um, by the way, yes. So I wanted to mention here, I left it as a note for myself. So the I plots, which we use to measure the RX side, you can use it for the TX side, but in this case, it's going to be like a system tools. They also want to see if we are receiving an eye, clean eye, for example, from the host, by the time it reach the chip inside the transceiver, what is it going to look like? What is the jitter? What is this? So you can use also the eye formulas graphs to do your investigations on the TX side, but looking from the transceiver, looking from inside. And the most important group is by far the crosstalk. The nightmare of all system engineer and RF engineer is the crosstalk. How to eliminate crosstalk, how to know, how to keep it under control. Let's call it that way. So they want to know about it. And crosstalk, there are so many kinds. There is what we call the absolute value, there is the relative value, and there is also, we added what we call the integrated crosstalk. Integrated crosstalk is almost like the average, because what they're going to ask you is to integrate the crosstalk across the whole band and divide it over the frequency, and that will tell them how much exactly will be the severe, the worst possible crosstalk from one channel to another channel. So in this case, it's between only the two lines that we are simulating. Later on, as I said, on the 8 model, it will be between the 8 lines of the RX, and on the 16 model, it will also include the RX and the TX crosstalk. So these system tools are important. That's why we added them. Now we go to the debugging tool. This is my favorite part. I will try to use whatever time is available to me. I think I have only a few minutes, but I need to show you guys the debugging tools. This is the niche of this template. This would distinguish this template from others, that it has and it will have even more. There are lots that we are working on now, debugging tools. And I will start with the most important one, which is debugging crosstalk. Let me show it to you in HFSS. It will be easy to explain it in HFSS in Circuit Designer. So crosstalk is a nightmare. It's our nightmare. We need to be able, as RF engineers, to identify where the crosstalk is coming from, which section of our circuit is the main contributor. The tool that we built here for you. So let me show it to you in the Circuit Designer here. Oh, sorry. Apologies. I forgot something there. So these two circuits that you see here are the ones that are going to answer this question for you. Okay. One of them is about the differential crosstalk, and the other one about the common mode crosstalk. So what do I do here? So if I open the graph, bear with me a little bit. I'm trying to find debugging. Yeah, debugging crosstalk. So what do you see here? What exactly? So let me. Okay, I need the circuit to show it to you. So the circuit, I don't know if you guys have seen it before. It looks familiar. It is the one that we use to do TDR. So everything has been set up for you here. You don't need to do anything. As I said, you just need to plug your model and you need to run it. So this part here, it will do the TDR of the input section, which we call the aggressor. So I go here and I plot my aggressor, which is the blue one that you see here, the blue one. And this will tell me, of course, as you can tell from the scaling here, it will tell me what's the impedance across my line. It will tell me what's going on within my line. And by looking at the different sections and how it moves, I can identify the different transitions within my model. But on top of this, I am plotting another curve. This other curve, I am taking it from the near end crosstalk. This is very important. So I'm not taking it from the far end crosstalk. I'm taking it from the near end crosstalk. In fact, you see here that what I did here is I terminated my far end ports, both of them. I cannot use them to debug crosstalk. Back to the curves. So if I go to the curves here, what is this showing me the other one? It's showing me exactly where the crosstalk is happening. In fact, it's telling me which part of my section is the main contributor. So for me, because these models that I was built, there was not that much crosstalk. So I created another model and I intentionally made it bad to see the crosstalk. So what is this model? Let me show it to you. If I hide this, okay. So let me make yeah, I can show it to you here. So it's a simple 2 transmission lines that you see here. And what I did is I intentionally removed the ground and the vias in the middle. And I said, run and show me. I want to be able to tell that the crosstalk is happening in the middle. And that's exactly what this graph is telling me. It's telling me it's happening in the middle. Not only that, the graph is telling me that most of the crosstalk is happening at the beginning here and at the end. But in the middle, yes, I have a crosstalk higher than the rest, but the main contributor are the edges. And guess, so now when you put your own and you are checking, you can tell from where the crosstalk is coming. Now, the good news is that this same circuit, you can remove this and you can replace it with your measurements. But now you understand that what you need to do is you need to measure the near end crosstalk, not the far end. The far end, you just terminate them. You don't need them. You just measure the near end crosstalk. You bring your measurement to this tool, to this template, you plug it, and it will tell you where is the crosstalk happening within your structure. Very nice, neat. Now we have a one for the, as I said, for the differential, and we have another one for the common. Please look at both of them, because as you know, as an RF engineer, you know that the field distribution of the differential is different than the field distribution of the common. The one of the differential is centered between the two signals. The one of the common uses the ground. So one of them is telling you about how good your differential lines. The other one is telling you about the grounds. How are they doing? If there's a problem with the grounds, it's going to tell you. So you need to look at both of them. Each one of them has its own signatures, and you need to learn about them. And if you master them, then crosstalk will no longer be a nightmare for you. You will be the master. You will be able to answer any question about crosstalk with 100% confidence, whether, as I said, during design or doing the measurements. Now, optimizing it, that's another thing. The only hint I want to give here to you, please, when you optimize your crosstalk, if you try to optimize the big one and it didn't work because you run out of options because of the dimensions, please go after the small ones. You will be surprised. Maybe sometimes suppressing the small ones will make you pass the spec. That's the advice I wanted to mention. So this is one of the debugging tools. We have things related to the rising time. Practically, when you do rising time, you have a bandwidth, and you have and you want to know what is the maximum rising time I can have. So if I use something smaller than that, I know for sure it's not going to go through. The traces will increase the rising time because of the bandwidth. So jitter, something else about jitter. Again, let me just fix my stuff here so I can be able. Jitter. Jitter is a debugging tool again. And as I say, and it's a big topic. We need like days to talk about it. But I wanted to show you what HFSS can do when it comes to debugging jitter. Jitter in HFSS, let me show you HFSS. It will be sometimes it's much better to show it in HFSS than to talk about it. So the circuit that we are talking about is this circuit that you see here, where I'm using the eye diagrams. So I have an eye source and we have an eye probe. And by the way, you can remove these ones and you can replace them with IBIS models. If you have IBIS model, you can use them. But if you don't have an IBIS model, what do? Don't panic. You come here, we have these ones, and you can do a lot with them. So I can go to the TXX. Remember, this is we are now looking from the RX side. We are looking at the transceiver. So here I can specify the maximum voltage, the minimum voltage. I can specify so many things. I can also add jitter. I can add jitter, and we have all kinds of jitter, DCD, random, pseudo noise, name it. So you can add, and the reason why you would do that is you want to see if my chip, the chip inside the transceiver has some sort of defections or limitations and producing some sort of is adding additional jitter to the nice clean eye. What do I expect to see here? So this is something you can use. But that's not all what HFSS can do for you. HFSS can also allow you to add jitter at the RX side. And by adding jitter at the RX side, you ask yourself, why do I need to add a jitter at the RX side? It doesn't go through my model. It's just added here. It is for measurement debugging. It's you measure your eye diagram and you see certain sort of jitters on it, and you have no idea what are they. The first thing you ask yourself is, what kind of jitter I have there? That's the first thing you need an answer to that, because without knowing what kind of jitter, you will not be able to tell from where it's coming from. So you need to know that. So the way we do it is when we do our plot. Let me show here. And I demand, for example, the verify eye on the bathtub. You see here, it says distribution. You say jitter. And you can edit it and you can add these ones as well as adding noise, but it's mainly adding this. So you start adding, and as you know, each one of them creates a specific signature on your bathtub. And by detecting these, like usually I add one at a time just to not to mix things. If it doesn't work, then I start adding more, two of them at a time, and play with the numbers. Once you see the signature and you match it to the same signature you saw it in measurement, you will be able to tell what exactly is damaging your measurement. So it's more of a tool used when we do a measurement. So you have both options, this option and that option. Um, so the last thing I wanted to, yeah, I am running out of time, so I'm going to use it to talk about the last part, is equalization. The standards, again, we go back to the standards, talks about that you are allowed to do certain equalization at the receiver side when you are measuring the transceiver, the receiver lanes. And the way we do debugging is using CTLE, which is continuous time linear equalizer, plus DFE. and the spec allows us up to 3 dB gain when we are doing the measurement of what we call the near end spec. But also the standards is asking us to measure the same receiver with an additional loss of 6.875 at 26 gig. But in this case, it's allowing us to introduce a CTLE with up to 9 dB. For those of you who do not know what CTLE and DFE, CTLE mainly compensate for the insertion loss. DFE is mainly to compensate for any memory that exists inside your model. And when we talk about memory, we're talking about some reflections happening within your model. So you see ripples in the insertion. And these ripples, the more you have, it means the longer is the memory of your structure. It's keeping information from an old bits, and it's passing them with the new one. So the job of the DFA is to try to correct for that. So that's why it's not recommended to do CTLE alone. It has to be CTLE plus the DFA. Again, I will go back to HFSS. As I said, I'm trying to spice things. So, so the way we do it here is we go to the eye, to our receiver. And immediately, the moment you open it, you will see them here, CTLE, and you can enter the poles, first pole, second pole, and the 0. At the same time, you can add the DFE. You specify how many tabs you want. So I'm going to put a number. It's going to ruin my simulation, but just for the sake of presentation, I will enter the number. I can ask HFSS to calculate the right weights for me for these tabs, and it will do it for you to improve to improve the eye. Then once you specify these two, for example, this way I say add DC blah 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 blah, enter CTLE. Okay, it didn't accept my sorry, I apologize. So add value. I'm doing something to CTLE. Maybe I terminated CTLE. Anyways, so there's a glitch here I have here. You choose your CTLE and you enter it here. And sometimes some people get scared from the CTLE. Like, how do I specify the CTLE? So the way to do it is we have a circuit in HFSS that will allow you to do that. And this circuit is, I found it. I was looking for it. It's this one. This simple circuit. So you can upload this component from the library, and you just add ports to it. And the beauty of this one is that if you double click on it, you can enter the values and the one that you want, and by entering these numbers, you will get a curve. So you keep playing until you get the numbers that matches what you want. Like, for example, here I needed like 1.75 dB of gain at 20 gig, between 20 gig and 25. So I entered these poles, and that's the one I used in order to change my eye. And I'm going to show you here an example where I have an eye that has like 0.2176 kind of width and 41. Suddenly, by doing the CTLA, you see the numbers get way much better. So it becomes 25 instead of 21, and then 69 instead of 41. It opened the eye. So that's the job of the CTLA and DFE. So as you can see, there are plenty of stuff that you can do with this template and within HFSS, and you can, as I said, we're going to add more to it in the future, but you can explore it, you can take it, you can download this template for free, you can play with it, you can even, the circuits, you can add more circuits. You're going to learn a lot from the formulas that we added, whether formulas related to the graphs or related to the limit lines, and hopefully it will be helpful to you. And keep checking for updates. We're trying to upload this template to our website. If you need it very fast, just send me your email and I will be able to share it with you. But there will be updates, and please check for these updates. I'm going to stop here because I think I used too much time. I don't know how much time we're left for questions.